Hello everyone, welcome to Chemistry Academy. This is episode 29 for JEE Advanced Problem Series, and today we are going to discuss a problem based on van der Waals real gas equation. So it's a very relevant problem according to our JEE Advanced syllabus, and this has been taken from International Chemistry Olympiad. So before starting the episode, I will like you to please share about our app in your circle. यदि आप हमारे चैनल पे नए हैं, आपने हमारे चैनल को सब्सक्राइब नहीं किया है तो प्लीज़ उसको सब्सक्राइब करें, और अगर आपको वीडियो पसंद आता है तो उसको लाइक करें। तो चलिए शुरू करते हैं एपिसोड 29। सो दिस इज़ अ प्रॉब्लम 2 ऑफ van der Waals real gas and this problem has 5 parts. It is divided into A, B, C, D and E part. So one by one we are going through the problem and then we'll solve it. So the first part here is the ideal gas equation PV is equal to nRT implies that the compressibility factor Z is equal to PV upon nRT is equal to 1. However, the compressibility factor is known to deviate from 1 for real gas. In order to account for the behavior of real gases, van der Waals propose the following equation of the state. So we know that van der Waals real gas equation is P plus n square A upon V square V minus NB is equal to nRT, where A and B are constant. These are characteristic constant of the gas, and A is related to intermolecular force of attraction and B is related to the size of real gas molecules. So already we know that A and B for a particular gas is not going to vary with temperature, pressure and volume, but for different gases the value of A and B is different. So coming to the first part of the problem, it has 3 parts. So I'm going through these problems and then one by one we are going to solve it. So let me go through all the 5 parts of the problem. So the first part is show on the basis of van der Waals equation that at sufficiently high temperatures Z is greater than unity for all pressures. At high temperature and low pressure Z approaches the value of an ideal gas, means Z is equal to 1. Then the second part is at lower temperature Z can be less than unity, and the third part for A is equal to 0, Z increases linearly with pressure. So in this A part, they want to know that how the value of Z is going to vary with pressure and temperature. Then in the B part of the problem, at a certain temperature, the variation of Z versus pressure for helium and nitrogen is shown systematically in the following figure, and the value of A and B for nitrogen and helium is given, and from there we have to find that which graph is for helium and which graph is for nitrogen. Then the third part of the problem, C part, is two pressure versus volume isotherms for van der Waals gas as shown below systematically. Identify the one that corresponds to a pressure lower than the critical temperature of the gas. So what is the importance of critical temperature we are going to discuss in this part of the problem. Then the D part is for a given P, the 3 roots of van der Waals gas equation in volume coincide at a certain temperature Tc. Determine Tc in terms of A and B and use the result to show that nitrogen liquefied more easily than helium. So this part is regarding that what is the importance of critical temperature. If the gas is at critical temperature or above critical temperature or below critical temperature, what conclusions we can make about the critical temperature. Then the last part of the problem is determine the work done by 1 mole of nitrogen gas when it expands reversibly and isothermally at 300 Kelvin from 1 liter to 10 liter, treating it as a van der Waals gas. So this is regarding thermodynamics, work done in isothermal reversible process. So let us start the problem one by one. So we are starting with the first problem, that is show on the basis of van der Waals equation that at sufficiently high temperature Z is greater than unity for all pressures. At high temperature and low pressure Z approaches the value of an ideal gas. So regarding this problem, we first write that what is van der Waals real gas equation. So for n is equal to 1 number of moles, we can write that P plus N square A upon V square. So P plus A upon V square, V minus nRT, N is equal to 1, so V minus NB, right? So N is equal to 1. So V minus B is equal to nRT, N is equal to 1. We can write van der Waals equation for 1 mole of a van der Waals real gas in this form. And if we open the bracket and try to simplify this problem, we can write that PV plus A by V minus PB minus AB upon V square is equal to RT. If we bring this RT on the left hand side, we can write that PV upon RT plus A upon VRT minus PB upon RT minus AB upon V square into RT is equal to 1. And PV upon RT for 1 mole of gas is compressibility factor Z, right? So we can write here that for van der Waals real gas, in general, Z can be written as 1 minus A upon VRT plus PB upon RT plus AB upon V square into RT. So this is the form of van der Waals real gas equation. Now they are saying that at sufficiently high temperature, Z is greater than unity for all pressure. So we can prove this with the help of this particular equation, or we can write the virile equation. That will be more useful, more easy to explain. So if we write van der Waals real gas equation in terms of virile equation, we know that in terms of virile equation for any real gas, we write Z as 1 plus B by V plus C by V square plus D by V cube up to infinity. So this is an virile equation for any real gas. When we discuss the same equation for van der Waals real gas, for van der Waals real gas, this equation can be simplified, and we can write the van der Waals real gas for the virile equation in terms of van der Waals real gas in this form. Z is equal to 1 plus B minus A upon RT 1 by V plus B square upon V square plus B cube upon V cube, and so on. So from here it's more easy. If we say that in low pressure range, these higher terms can be neglected. So if we neglect the higher terms, we can write that Z is equal to 1 plus B minus A upon RT 1 by V. Like here in the first part of the problem, they are asking that prove that at higher temperature Z is greater than 1. So we can say that from here, if we are increasing the temperature, the value of A upon RT is going to decrease. So at higher temperature, this value will be smaller than B. So this whole thing is going to positive. This is known as virile second coefficient, which is positive. So if the virile second coefficient is positive and the other terms are positive, we can prove that when the temperature is high, at high temperature, we can say that Z is always greater than 1 for a van der Waals real gas, right? So using this equation, we can write here, they are asking that at sufficiently high temperature, Z is greater than unity for all pressure. That can be proved with the help of virile equation. विराइल इक्वेशन में अभी हमने van der Waals रियल गैस के लिए लिखा कि Z को हम लिख सकते हैं Z इज इक्वल टू 1 प्लस B माइनस A अपॉन RT 1 by V plus B square upon V square plus B cube upon V cube up to infinite. And we know that when the temperature is equal to Boyle's temperature, virile second coefficient is equal to 0. So when the temperature is greater than Boyle's temperature, virile second coefficient is going to be positive. and the higher coefficients are always positive. So from here we can say that when the temperature of the gas is greater than Boyle's temperature, the value of Z is always greater than 1 for a van der Waal real gas. The second part is at high temperature and low pressure, Z approaches the value for an ideal gas, right? Means Z approaches 1. That can also be proved by two ways. Like here from the first equation we can say that when the temperature is high, right? So when the temperature is high and pressure is low, right? So when P is low means volume is large, so P is low means volume is large, and temperature is high. So from here we can say that the denominator, both volume and temperature is high, so we can neglect this part, right? We can say that under this condition this is going to be 0. And again here when the pressure is low and temperature is high, this portion can also be neglected with respect to 1. And here again, because the volume is large and temperature is high, this portion is also going to be 0. From there we can say that Z is equal to 1. So we are discussing that there is another way to prove the same thing by using a virile equation. In low pressure range, the higher terms can be neglected, right? So in low pressure range we neglect all these higher terms, and when the temperature is high, right? So in low pressure range we are neglecting all these terms, and we can say that in high temperature and low pressure means again we can neglect this term, right? So this whole term can be neglected, and we can say that Z is equal to 1. So very high temperature and low pressure, we can say that a real gas will behave like an ideal gas, and there is two ways to prove the same. Once using this equation or using virile equation also we are able to prove the same thing. So here it is shown that for the same real gas, when the gas is at Boyle's temperature, here this graph is at Boyle's temperature, so at Boyle's temperature in low pressure range the gas is behaving like an ideal gas, and then after that Z is greater than 1. And at high temperature, when the temperature is greater than Boyle's temperature, we can say that in all range Z is greater than 1. And we can say here that when the temperature of the gas is below the Boyle's temperature, we can say that for most of the pressure the value of Z is less than 1. The value of Z is less than 1 indicating that the force of attraction is dominating, right? And in high pressure range again the force of repulsion is going to dominate. So these three things are important. When the temperature of the gas is above its Boyle's temperature, we can say that if this condition is there in all pressure range, Z is greater than 1. Then when the temperature of the gas is equals to Boyle's temperature, we can say that in low pressure range Z is equal to 1. So in low pressure range, when pressure is low, we can say Z is equal to 1. Pressure is low means when the pressure is near about 1 atm or below 1 atm, then we are discussing that. And when the pressure is high, again we can say that Z is greater than 1. And the third part is when the temperature is below the Boyle's temperature, for most of the time we can say that Z is less than 1. So in low pressure range or intermediate pressure range, in a large range of pressure we'll say that attractive forces are dominating. And we can also say that in this also when the pressure is very high, then Z is greater than 1, we are discussing over here. So that is about the interactive forces variation with temperature and pressure for van der Waal real gas. Before moving to the second part of the question, these graphs are given in NCERT. So you can see here that for hydrogen and helium gas, for these gases in all pressure range, Z is greater than 1. Here this is PV versus P graph, but the similar type of graph we can obtain when we draw PV upon RT versus P, right? So these are isotherm. So we can say that for hydrogen and helium gas in all pressure range, the value of Z is greater than 1, because for hydrogen and helium, the value of A is very small. And for carbon monoxide and CH4 gas, we can say that the temperature of these gases are below at room temperature. I think this graph is there. At about 273 Kelvin, this graph is there. So we can say that at 273 Kelvin, the temperature is lower than its Boyle's temperature, and that's why attractive forces are dominating. From here also they can ask a question that it is easy to liquefy which gas. So lower value of Z means more force of attraction. If the value of Z is less than 1, it means that there is force of attraction is dominating. So more less value than 1 means more force of attraction, means easy to liquefy the gas. So from this graph we can say that CH4 is more easy to liquefy with respect to carbon monoxide, and we cannot liquefy hydrogen and helium gas at 273 Kelvin, because at this temperature Z is always greater than 1, means repulsive forces are dominating in case of hydrogen and helium. So moving to the next part, second part of the first problem, show on the basis of van der Waals equation that at lower temperature Z can be less than unity. We have already discussed at lower temperature Z is less than unity. If I am writing virile equation for van der Waals gas, we can write that Z is equal to 1 plus B minus A upon RT 1 by V plus B square upon V square plus B cube upon V cube. So it's not always that in low temperature range Z is always less than unity. They are saying Z can be less than unity at lower temperature. That we have to understand. When we are saying that pressure is low and temperature is also low, right? When pressure and temperature both is low, at low pressure we can neglect the higher terms. So we can write that Z is equal to 1 plus B minus A upon RT 1 by V. And when the temperature is below the Boyle's temperature, then we can say that this virile second coefficient will be negative, will be less than 0. And from there we can say that Z is less than 1 for a van der Waals real gas at low temperature, when the temperature is below its Boyle's temperature and we are in low pressure range, then we can say that Z is less than 1. अभी हमने थोड़ी देर पहले ये डिस्कस किया था Z वर्सेस P ग्राफ में. आप यहाँ देख सकते हो, जैसे यहाँ पे this is related to the temperature greater than Boyle's temperature. This is for the same gas at different temperature. Plots of PV upon nRT versus P for nitrogen gas at 3 different temperatures, right? So this temperature is above Boyle's temperature and this graph is at Boyle's temperature, and we can say that this graph is below the Boyle's temperature. So we can say that this temperature 203 is below Boyle's temperature, right? This Boyle's temperature is greater than 203 Kelvin. So from here we can say that I can write like this: T is 203 Kelvin, which is less than Boyle's temperature. So under this condition, यहाँ पे देखें अगर तो from here to here the value of Z is less than 1, and when the value of Z is less than 1 means attractive forces are dominating. ठीक है, तो ये second point हो गया. इसमें हमें ये समझना है कि ऐसा है कि अगर टेम्परेचर बॉयल्स टेम्परेचर के नीचे है तो लो प्रेशर रेंज में या इंटरमीडिएट प्रेशर रेंज में द वैल्यू ऑफ Z इज लेस देन 1, बट इट इज नॉट ऑलवेज दैट when the temperature is below Boyle's temperature always Z value is less than 1. When the pressure is high, then we can say that the Z value is going to be greater than 1. So high pressure range में low temperature पे भी repulsive forces are going to dominate. Moving to the third part, show on the basis of van der Waals equation that for A is equal to 0, Z increases linearly with pressure. तो van der Waals रियल गैस इक्वेशन में 1 मोल गैस के लिए लिख रहा हूँ, n is equal to 1. वी कैन राइट दैट P plus n square a upon v square, v minus b is equal to RT. So from here, when a is 0, we can say that this term will be 0, and from there we can write that PV minus PB is equal to RT. If I take RT on the left hand side, I can write that PV upon RT minus PB upon RT is equal to 1. If I simplify further, we can write that Z is equal to 1 plus PB upon RT. So when the temperature is constant, we can say here that when temperature is constant, on increasing pressure, increase in pressure will increase the value of Z, and we can say that on increasing pressure Z is going to be linearly vary, right? So this A value is negligible for hydrogen and helium gas. For hydrogen and helium gas, we can say that the value of A is negligible, so Z is equal to 1 plus PB upon RT. So near about room temperature or 273 Kelvin, we can say that for hydrogen and helium gas, Z is always greater than 1. Z is always greater than unity, means repulsive forces are dominating over the temperature near about room temperature or 273 Kelvin, right? So it's हाइड्रोजन एंड हीलियम को हम परमानेंट गैसेस भी इसी वजह से कहते हैं क्योंकि रूम टेम्परेचर या उसके आसपास 0 डिग्री सेल्सियस से लेके 25 डिग्री सेल्सियस इसके आसपास के टेम्परेचर पे repulsive forces are going to dominate and we are not able to liquefy the gas. But it doesn't mean that we cannot liquefy hydrogen and helium gas. We can liquefy hydrogen and helium gas. We have to put the temperature very low. When we bring hydrogen and helium below their critical temperature or up to critical temperature, then we are able to liquefy the gas. And the critical temperature for helium is about 4 Kelvin, right? So critical temperature is very low, so it's very difficult to liquefy helium and hydrogen gas, but we can liquefy them. The B part of this question, at a certain temperature the variation of Z versus P for helium and nitrogen is shown systematically, and from here we have to find that कौन सा ग्राफ किसके लिए है. तो आप देखिए हीलियम के लिए ए की वैल्यू जो है वो काफ़ी छोटी दे रखी है विथ रिस्पेक्ट टू नाइट्रोजन. सो आई कैन नेग्लेक्ट द वैल्यू ऑफ ए, और जैसे ही मैं हीलियम के लिए ए की वैल्यू नेग्लेक्ट करूंगा आई कैन राइट दैट जेड इज इक्वल टू 1 प्लस पी बी अपॉन आर टी. सो जेड वर्सेस पी ग्राफ में इट इज गोइंग टू बी अ स्ट्रेट लाइन, लीनियर वेरिएशन, राइट. दिस इज जेड इज इक्वल टू 1 और यहाँ से ये लीनियर वेरिएशन जो है वो हीलियम गैस के लिए होगा. सो फ्रॉम हियर वी कैन से दैट दिस ग्राफ इज फॉर हीलियम एंड दिस ग्राफ इज फॉर नाइट्रोजन. सो अंडर द गिवन कंडीशन ऑफ टेम्परेचर वी कैन से दैट यहाँ पे नाइट्रोजन का जो टेम्परेचर होगा, दिस टेम्परेचर इज बिलो इट्स बॉयल्स टेम्परेचर बिकॉज in low pressure range Z is less than 1 means attractive forces are dominating. That is indicating that the gas temperature is below its Boyle's temperature. कुछ बच्चों को ऐसा लगता है कि if Z is less than 1 we can liquefy the gas. That is a wrong thing. When Z is less than 1 is indicating that force of attraction is dominating, but force of attraction should dominate is necessary condition, but it is not the sufficient condition for liquefaction of the gas. It should also overcome the thermal energy, then only the gas can be liquefied. So if the gas temperature is up to its critical temperature or below its critical temperature, then we'll say that thermal energy is low and attractive forces can overcome thermal energy and the gas can be liquefied. तो हमने पढ़ा है कि गैस को लिक्विफाई करने के लिए वो जो मैक्सिमम टेम्परेचर जहाँ तक गैस को हम लिक्विफाई कर सकते हैं, दैट टेम्परेचर इज क्रिटिकल टेम्परेचर, और द मिनिमम टेम्परेचर अबव विच द गैस कैन नॉट बी लिक्विफाई इज क्रिटिकल टेम्परेचर. तो ये क्वेश्चन बार बार पूछा जाता है, आपको पता होना चाहिए कि अगर गैस का टेम्परेचर बॉयल्स टेम्परेचर के नीचे है तो Z इज लेस देन 1 इन लो प्रेशर रेंज, नॉट इन ऑल प्रेशर रेंज. सेकेंड पॉइंट, अगर Z की वैल्यू 1 से कम है तो फोर्स ऑफ अट्रैक्शन डोमिनेटिंग है, but force of attraction dominating is not sufficient condition, right? मतलब अगर टेम्परेचर बॉयल्स टेम्परेचर के नीचे है और क्रिटिकल टेम्परेचर से ऊपर है, देन हम गैस को लिक्विफाई नहीं कर सकते, क्योंकि आपने वेंडरवॉल रियल गैस के लिए जब आप बॉयल्स टेम्परेचर की वैल्यू कैलकुलेट करते हो, बॉयल्स टेम्परेचर फॉर वेंडरवॉल रियल गैस इज इक्वल टू A upon BR, and when we calculate critical temperature, that is very low, 8 upon 27 times A upon BR, right? तो बॉयल्स टेम्परेचर से क्रिटिकल टेम्परेचर बहुत छोटा है. सो व्हेन वी आर सेइंग दैट वी आर इन लो प्रेशर रेंज, हम अगर लो प्रेशर रेंज के अंदर हैं एंड द टेम्परेचर इज above the critical temperature and below the boils temperature, under this condition we cannot liquefy the gas. So that is also an important point to learn here. Moving to the third part of the question, two pressure versus volume isotherm for van der Waal gas are shown below. Systematically identify the one that correspond to a temperature lower than the critical temperature of the gas. तो इसको देखने का एक तरीका ये है कि when we have discussed about critical constant, how we have derived about critical constant, right? तो हमने critical constant को कैसे derive कर रखा है. अगर आप वेंडरवॉल रियल इक्वेशन को देखो, P plus N square A upon V square, when N is equal to 1, we can write that this is P up plus A upon V square, V minus B is equal to RT. अगर मैं इसको और सिंप्लीफाई करूं, it is a cubic equation in volume. I can write here that pressure into volume square plus A V minus B is equal to V square into RT. So when I simplify, we can say that it is a cubic equation in volume. And when we are discussing about this cubic equation, at a particular temperature, temperature is fixed, right? For a fixed value of temperature and fixed value of pressure, अगर हम temperature और pressure को fix कर दें, so you can see here that कि ये जो equation है, when the temperature is below the critical temperature, then the graph, अगर मैं relate करूं जो बना, वो इस तरह का graph होगा. If I try to relate it with cubic equation, this is the graph when the temperature is below critical temperature. So here in this, if we try to find out under the condition when the temperature is below critical temperature, in this cubic equation we can say there are three roots, but इसमें से one root is real, and two roots are imaginary. तो अगर गैस का टेम्परेचर क्रिटिकल टेम्परेचर से कम है, फॉर अ फिक्स वैल्यू ऑफ प्रेशर, गैस के तीन रूट्स होने चाहिए, जिसमें से दो इमेजनरी हैं और एक रियल रूट है. व्हेन वी आर गोइंग टू इंक्रीज द टेम्परेचर, और जब हम क्रिटिकल टेम्परेचर पे पहुंच जाएंगे, व्हेन वी आर गोइंग टू रीच द क्रिटिकल टेम्परेचर, we can say that at critical temperature, when pressure is equal to Pc, temperature is equal to Tc, then we can say that all the three roots are real and equal. तीनों रूट्स जो हैं वो रियल होंगे और इक्वल होंगे. अंडर दैट कंडीशन वी कैन से दैट V minus Vc whole cube is equal to 0. And if we try to equate these equations, from these equations we can derive the value of critical pressure, critical temperature and critical volume. जैसे हमें पता है कि वेंडरवॉल रियल गैस के लिए अगर हम इस मेथड से क्रिटिकल टेम्परेचर कैलकुलेट करते हैं, दैट इज 8 upon 27 A upon BR. If we calculate what is the value of critical pressure, that is 1 upon 27 A upon B square, and critical volume is 3 times of B. So the value of critical constant for van der Waal real gas can be calculated by this method, right? So we can say here that here the temperature T1 is greater than critical temperature, and here the temperature T2 is less than critical temperature. और अगर क्रिटिकल टेम्परेचर होगा तो दिस ग्राफ इज लाइक दिस, देयर इज अ इन्फ्लेक्शन पॉइंट ओवर हियर, यहाँ पे इन्फ्लेक्शन पॉइंट होगा, मीन्स वी कैन से दैट द वेरिएशन ऑफ स्लोप dp अपॉन dv, स्लोप की वैल्यू जो है एट अ क्रिटिकल प्रेशर एंड क्रिटिकल टेम्परेचर शुड बी इक्वल टू 0 एंड the rate of change of slope is also 0, d square p upon dv square at critical temperature and critical pressure should also be equals to 0. So this is also a way to calculate the value of critical constant for any real gas. For van der Waals real gas, the value of critical constant का formula हमने जो calculate किया है, maybe for another real gas it is going to vary. This is the method of derivation how we derive the value of critical constant for a real gas. तो इसमें इंपॉर्टेंट क्या है, किसी सब्सटेंस का जो क्रिटिकल पॉइंट है वो चेंज नहीं होता, क्रिटिकल टेम्परेचर, क्रिटिकल प्रेशर एंड क्रिटिकल वॉल्यूम इज नॉट गोइंग टू चेंज, बॉइलिंग पॉइंट इज वेरिएबल, राइट, मेल्टिंग पॉइंट इज वेरिएबल, बट क्रिटिकल पॉइंट फॉर अ सब्सटेंस इज नॉट गोइंग टू वेरी. दैट्स व्हाई जेईई एडवांस में एक बार क्वेश्चन पूछा गया था कि वैन डर वाल रियल गैस के लिए ए और बी की वैल्यू टेम्परेचर और प्रेशर के साथ क्या वेरी करेगी? नो, बिकॉज when we calculate the value of A and B, we calculate the value of A and B with the help of critical constant. TC, PC की मदद से हम A और B की वैल्यू कैलकुलेट करते हैं, और TC और PC किसी सब्सटेंस का चेंज नहीं हो सकता. That's why for a particular van der Waals gas, the value of A and B is independent of temperature and pressure. So this is we have discussed that for van der Waals real gas, this is critical temperature, critical pressure, critical volume, how we can derive at critical point there is an inflection point, so the slope will be 0 at that point, or the rate of change of slope will be 0 at that point. With the help of these two we can calculate what is critical temperature, critical pressure and critical volume. Another way is that कि क्रिटिकल पॉइंट पे जो क्यूबिक इक्वेशन है उसके तीनों रूट्स बराबर होंगे एंड रियल होंगे. सो फ्रॉम देयर वी कैन ऑल्सो फाइंड आउट दैट व्हाट इज द वैल्यू ऑफ क्रिटिकल कॉन्स्टेंट्स. D part, for a given pressure, the three roots of van der Waals equation in volume coincide at a certain temperature. T is equal to Tc. Determine Tc in terms of A and B and use the result to show that nitrogen is liquefied more readily than helium. So already we know that for van der Waals real gas, either we can derive the critical temperature by putting slope and rate of change of slope is equal to 0 at inflection point, जहाँ अभी यहाँ पे जो solve कर रखा है वो इस method से, या दूसरा method है v minus vc whole cube is equal to 0 and we'll equate this to van der Waals real gas equation. From there we can find out. So for van der Waals real gas we know that critical temperature is equal to 8 upon 27 A upon Br. The value of A and B for helium and nitrogen gas is given, right? And from there we have find out A और B की value रखेंगे तो we are getting that the value of A and B for helium is this and the value of A and B for nitrogen is this. If we put in this equation of critical temperature, we are getting that critical temperature for helium gas is 5.2 Kelvin and critical temperature for नाइट्रोजन गैस इज 128 केल्विन. जिस गैस का क्रिटिकल टेम्परेचर ज़्यादा होगा मतलब उस टेम्परेचर तक हम गैस को लिक्विफाई कर सकते हैं, मतलब ज़्यादा टेम्परेचर तक गैस में अट्रैक्टिव फोर्सेस डोमिनेट हो सकते हैं, राइट? सो इट इज़ मोर इजी टू लिक्विफाई दैट गैस हुज क्रिटिकल टेम्परेचर इज हाई. इस कॉन्सेप्ट का एप्लीकेशन हम सरफेस केमिस्ट्री में भी करते हैं कि जिस गैस का क्रिटिकल टेम्परेचर हाई होता है उस गैस की बॉन्ड बनाने की टेंडेंसी ज़्यादा होती है, उस गैस के एड्जॉर्प्शन की टेंडेंसी ज़्यादा होती है. सो हाई एट द क्रिटिकल टेम्परेचर इट इज़ मोर इजी टू एड्जॉर्ब द गैस, राइट, और मोर इजी टू लिक्विफाई द गैस. सो हियर वी कैन से दैट नाइट्रोजन गैस को लिक्विफाई करना आसान है विथ रिस्पेक्ट टू हीलियम गैस. ठीक है, मूविंग टू द ई पार्ट. डिटरमाइन द वर्क डन बाई 1 mole of nitrogen gas when it is expand reversibly and isothermally at 300 Kelvin from 1 liter to 10 liter, treating it as a van der Waals real gas. किसी भी substance के लिए अगर हमें work done लिखना है according to IUPAC convention, dW is minus times of P external into dV. Physics में आप pressure of gas लिखते हो, right? but in chemistry we follow IUPAC convention. We'll write like this: P external is equal to the pressure of the system, because the difference between the driving force and opposing force is very small in case of reversible process. So here we are taking approximation that P external is equal to P of the system. वेंडरवॉल रियल गैस के लिए अगर n की वैल्यू 1 है तो प्रेशर को हम लिख सकते हैं RT V माइनस बी माइनस A upon V square. This is the variation of pressure with temperature and volume. So now if I put here external की जगह हम गैस का प्रेशर रख दें तो we can write here that dW is equal to minus times of pressure of the gas की जगह हम लिख सकते हैं RT V minus B minus A upon V square into dV. And now if we integrate both side, क्योंकि temperature constant है, we can write that dW is equal to minus RT, and here it will be dV V minus B. This minus and minus will be plus A dV upon V square. And now we are going to integrate. So we are moving from 1 liter, so V1 to V2 here. Here also we are moving from V1 to V2. So if we simplify this, अगर हम इसको simplify करते हैं तो we can write that work done in this process will be equal to minus RT. If we take integration of this, this should be ln V2 minus B upon V1 minus B. और इसका अगर हम इंटीग्रेशन करेंगे तो ये माइनस साइन आएगा, उसको सिंप्लीफाई करेंगे तो वी कैन राइट हियर दैट A 1 upon V1 minus 1 upon V2, right? So if we put the value of A and B and V1 and V2 along with temperature, we are going to get the work done during this process is minus 56.7 liter bar per mole. So here when we are going to use this, यहाँ पे आंसर लीटर बार में दे रखा है, तो R की वैल्यू हमें क्या यूज करनी चाहिए? When the pressure is in bar, the volume is in liter, temperature Kelvin में है, तो R की वैल्यू हमें यूज करनी चाहिए 0.08314. So when we put this value, temperature is already given, that is equal to 300 Kelvin. V2 is 10, V1 is 1, A and B is given for the nitrogen gas. Then we can calculate what is the work done during this isothermal reversible process. So what is the learning from this problem? इस प्रॉब्लम से हमने बहुत सारी चीज़ें सीखी. जैसे हमने ये सीखा कि अगर हम टेम्परेचर को बढ़ाते हैं तो गैस को लिक्विफाई करना मुश्किल होगा. अगर गैस का टेम्परेचर उसके बॉयल्स टेम्परेचर के ऊपर है तो Z की वैल्यू ग्रेटर देन 1 होगी and we cannot liquefy the gas. Then we have learned that when the temperature of the gas is boils temperature, then in low pressure range, for certain range of pressure, we can say that the value of Z is equal to 1, means the real gas is behaving like ideal gas. And when the temperature is below the boils temperature, for most of the pressure, we can say that Z is less than 1. And in high pressure range, Z again will be greater than 1. Right? Then we have learned that what is the importance of critical temperature. If the temperature of the gas is below critical temperature, then we can liquefy the gas, and if the temperature of the gas is above critical temperature and below boils temperature, then also we cannot liquefy the gas. Importance of A: when A is very small, like for hydrogen and helium gas, we can say that for hydrogen and helium gas, when A is very negligible, then we can write that Z is equal to 1 plus PB upon RT. So on increasing pressure, the value of Z is going to increase linearly, and for most of the pressures at near about room temperature, we can say that for hydrogen and helium, Z is greater than 1. So they are known as permanent gases and they cannot be liquefied. But it doesn't mean that hydrogen and helium cannot be liquefied. They can be liquefied if we put the temperature below their critical temperature. I have told you that the temperature, critical temperature for helium gas is very low, near about 4 Kelvin. In calculation, you have seen that in the last part, the temperature we have calculated, critical temperature is 5.2 Kelvin. So it's telling that हीलियम गैस, हाइड्रोजन और हीलियम में क्रिटिकल टेम्परेचर जो है वो हीलियम का हाइड्रोजन गैस से कम है. So from there also we can say that it is more easy to liquefy hydrogen gas with respect to helium gas. ठीक है, जिस गैस का क्रिटिकल टेम्परेचर ज़्यादा होगा उस गैस को लिक्विफाई करना आसान होगा. मैं ये उम्मीद करता हूँ कि आपको ये क्वेश्चन और ये प्रॉब्लम जो है वो पसंद आया होगा. अगर पसंद आया है तो वीडियो को लाइक करना ना भूलें, और ऐसे और वीडियोस के लिए और डिस्कशंस के लिए आप हमारे ऐप को डाउनलोड कर सकते हैं या हमारे चैनल को सब्सक्राइब कर सकते हैं. सो थैंक यू वेरी मच. बाय बाय.